Welcome back. A customer requested me to make him a bunch of carbide bushings. Means solid carbide. Means different set of challenges in machining than regular steels. Because normal tools don't cut it here. Literally. So what I need to do is I need to make bushings like this, about 10 millimeters long, 8 millimeter OD, and various sizes of bores on the ID. And also they need a radius ground or machined onto the entry of the bore on one side. My first idea was to look for a off-the-shelf part, like a carbide drill bushing, a carbide cutting bushing for tool and die, but I couldn't find anything that was remotely in a reasonable size combination that would work to be modified. So what I did instead is I purchased a carbide tooling blank, which already has a starting hole in the center, hole popped through it. These are done, in this case, since it's a straight through hole, through coolant hole, these are done on an EDM drill. That's like a ram EDM for sinking down contours into for example, mold parts, but a hole popper or a EDM drill is radically faster with a lot of increased electrode wear, like at least 1-to-1 ratio wear of the electrode to drill depth, but it's fast. So got this blank here, came from P-Horn. It's 8 millimeter OD and it's already ground to a nice finish on the OD and to a very close tolerance. It's slightly minus toleranced. So if you micrometer this, it shouldn't be too far off of 8 millimeters. So it's a few micron undersize. But I need to enlarge the bore in here. I don't have a good tool for that. So I reached out to a friend who has a wire EDM in his barn. I'm preparing a bunch of blanks, 40 millimeters long. He's going to wire the bores into it with few micron undersize so I can grind them on a lathe to final ID using high-speed spindle. Then using the CNC I will do the 3D grinding of the lead-in radius and then we will do some polishing. So basically not very complicated, but first we need to cut the blank into 40 millimeter length. That's what he told me to prepare because that's what he's comfortable doing on the machine he has. Okay, let's get the tool and cutter grinder prepared as a cutoff machine. First we need to reorient the tool head up here. On tool and cutter grinders you always get grinding dust on all the sliding surfaces. So make sure each time you move some of the accessories around on either the dovetails or T-slot table, whatever the machine is configured at, make sure to wipe it down before you move anything, otherwise you will get a horrendous amount of wear in a very short period of time. Also generally it's a good idea to keep machines as clean as possible. Just makes for a longer lasting experience. Changing the collet here to 8 millimeter collet, and I need to change the wheel. Also need to retract this a little bit and to change the wheel. You know, the large spanner wrench. Pop this loose. And we use a resin bond diamond wheel for the cutoff. Also we reorient the dust collection a little bit so we get most of it extracted. good to set up our cutoff. I'm setting it at about center height with the grinding wheel. Added a rubber band down here to automatically move the table to its origin position. I cut 5 pieces 40mm long each. I need 2 with a 2.1mm hole on the ID and 2 with a 4.1mm hole on the ID. Tolerances are loose-ish. There is nothing super critical. They just need to be nice. I cut 1 spare if something with the wire cutting goes wrong. Also, these are long enough so I can get 3 out of them and still have some stock to hold on to them for using the cutoff wheel. You notice that when I cut them off, there is a little bit of material left here. That's because I didn't support the carbide on both ends, and since it's very brittle, it tends to snap off on the last bit of material. It doesn't matter here, because these are way oversized anyways, but for the wire EDM it would be nice if the ends are flat, otherwise this could mess with the water flushing that needs to happen during wire EDM. There is a stream of water running down, or it's completely submerged in a bath, which that's what my buddy runs usually, but I was told it helps if the parts are flat on both sides. So I'm going to put these on the surface grinder in a V-block and just dust off the cutoff surface here. Got all 5 of the blanks squared up on the ends, and now I can ship them out to my friend to have them wire EDM'd. Of course, people always ask, oh, Stefan, when do you get a wire EDM? I won't. Wire EDM, even if it's not a good friend that's doing the work for you, wire EDM hours are not that expensive, and a wire EDM machine is a lot of stuff. It's the machine, it's the wire, it's the filters, it's the deionized water. It's a complete set of work holding that has to be non-corrosive. And it's a lot of stuff. That's why wire EDM shops exist. So let's pack it up. That's why I always keep the end mill containers for shipping small stuff like this. Give it the old shake test. That's fine. That's just the carbide in the plastic containers rattling around, but none of the actual packaging or containers itself are flopping around. So that's good. Off to the post office, and the parts are back from wire EDM. My friend cut them very close to nominal size, 4mm and 2mm ID. And he didn't need the spare one, so this goes back in the drawer. I have a 4mm carbide shank here. and so this is a close fit in here. So we have some material to work with. I'm going to ID grind it to final dimension. The wire EDM that he runs is a little bit on the older side, and he is hesitant to try to hit tight tolerances with it. Plus, the surface finish of wiring the bore is not as nice on an older machine as I would like to be. So that's the reason why I have them cut undersized and then grind them to final dimension. And here with a 2mm carbide shank, so 2mm, a little bit on the tight side. Yeah, I could push it through, but then it's tough to get out again. So yeah, this one is 2mm all the way through, but you can feel when you spin it that it's not round. Next, we cut it into 10mm long segments because that's the final length. Well, cut it slightly over size, and then surface grind them to final length. Cutting off the blanks in the tool and cutter grinder. Getting a rough length using a scale. Final length will be surface ground anyways. They just need to be a little bit longer. And I'm putting a pin inside the bushing. So when I break through the carbide, the cutoff piece doesn't snap off on a remaining thin section of carbide, and also it doesn't drop down into the dust extraction. Yes, it's a steel pin, and you shouldn't cut steel with a diamond cutoff wheel, but I'm only scratching into the steel, so shouldn't be a big problem. Also, this cutoff wheel does not want to behave at all. It tends to chatter a little bit. Not sure why. Here I'm just dusting off both ends of the carbide bushing blanks that I cut off on the tool and cutter grinder, just to make the end square. Here are all the blanks for the bushings. Cleaned up on both sides on the surface grinder just to square them up roughly before I do the ID grinding. I'm leaving them a little bit longer, so when I do my radius grind and I don't get the blend of the radius to the face of the part perfectly, I can still adjust by sinking the face down a little bit. And then I can grind it back to final length. I'm not a big fan of grinding on the lathe, especially for OD grinding. If the material can be cut with carbide or CBN, usually that's the better choice. Grinding on a lathe is only interesting if you're machining material or cutting material that's extremely tough to cut by regular cutting tools or impossible. You can machine carbide. I have shown cutting carbide, but that was an OD and it's sketchy at best. This is a case where grinding makes sense because we were working an ID of a part in carbide with a small diameter. And that's a very problematic situation that we can solve by ID grinding the best. Let's find some parts to build our ID grinding setup. And this is a collet sleeve that takes the collets from my decal milling machine. And this is an 18mm collet that goes in here. collet sleeve gets locked. And then I have my air-driven jig grinding spindle. This goes into this collet. This is normally meant to be used in a boring head of a milling machine, hence the rotating ring to supply air to it, so you don't tangle up the hose. But also it can be used stationary on a lathe. That's a mighty overhang, but I have used this setup before for ID grinding and it works okay. I would prefer to do it on the surface grinder because it's made for grinding, which the lathe is not. I need to remove the compound here because this is in the way, and also I don't want to get dust on it. I think it's good practice to plug up threaded holes in machine tools that are not used with either set screws or cap screws to keep dirt out and also make everything a little bit easier to be cleaned. So here we're grinding with a metal bond diamond tool. That means there is grains of diamond bonded with a galvanic applied layer of metal on a carrier, in this case a steel shank. The grinding spindle runs at about 30 to 40,000 RPM depending on the air pressure. And as you can see, once we're in the bore, we're just stroking back and forth with the diamond tool not exiting the bore completely on both ends. On the rear end, I have to use the DRO on the side that's facing towards me so I can see it. I can just eyeball it. If you go outside of the bore too far or completely with the grinding tool during the ID grinding while you're stroking the entire length of the bore, there is a high probability of bell mouthing the bore because you suddenly lose the pressure on the grinding tool, and then you end up with bell-mouthed contour, which we don't want. Here I'm checking the ID with the gauge pin. I find gauge pins to be the most reliable way of checking small bores. This is an overview. You can see on the left side the rear hose that goes to the through bore of the spindle. That's from my shop vac. And I'm basically using the shop vac through the spindle bore, through the collet chuck, and through the collet into the part to collect all the carbide dust. After I took everything apart, there was literally close to no carbide dust in the collet. I was surprised how easy it is with this setup to hit dimensions to size. The feedback loop from grinding to checking the ID of the bores with 10 micron incremented gauge pins is very short, and you can very quickly adjust, especially using the DRO. Did the ID grinding on all 8 of the bushings, and they came out pretty consistent. The 4.1 millimeter ones, when I take a 4.1 millimeter pin, it's a nice sliding fit in all of them. And if I try to take a 4.11 millimeter pin, that's 10 micron bigger, doesn't even start on any of the bushings. So that's more than adequate for these parts. To be honest, they don't have to be that accurate, but it's a good excuse to improve my skills and use this project as kind of a skill to get more confident in ID grinding. Same for the 2.1 millimeter bushings. 2.1 millimeter pin, sliding fit, and the 2.11 millimeter pin does not even want to start. So that went quite well. Off to the CNC to do the 3D grinding. And I even have 2 spares left. I don't think that I need them. These go in a box with carbide blanks if I need something with a hole anytime, or maybe a return order of these. Over on the CNC milling machine, this is the Arova 0-point chucking system. I removed the pallet that was in there before, and I'm changing to a more universal fixture plate that just has a grid pattern of threaded holes in it. With the Arova, we always make sure that the 4 pads on the chuck are clean, and then we can just drop our fixture in there. And it's all trammed and aligned with the ways. To hold the actual part, I'm using Adam's super low profile V-block that he made. He made a video on these. I will link the video down in the description. He sent one of them to me, and it's such a lovely tool. it's almost not funny how nicely it is made. And together with a small copper pad, the bushing can be clamped in the V-block without any damage. Well, damaging carbide with a steel screw would be tough anyways, but the second V and the copper pad is just a nice touch. Changing the tool in the spindle. Finding the center on the carbide bushing using the shop-made dial test indicator holder. Double checking, all good. From a design standpoint, I would say I would build this indicator holder just like that again without any changes. It really just works. This is the tool that I'm using to grind the lead-in radius on these bushings. It's a 2 millimeter ball diamond, like this, that you also would use in your die grinder for deburring or engraving. It's a D91 grit. It's a little bit finer than the cylindrical grinding tools that I used here. Ugh. These are D126, which is a little bit coarser. So here is the actual grinding process in real time. I start at the bottom of the radius with the ball tool, and then I take the entire radius in one go in a spiral tool path, removing a lot of material but doing an extremely small step over per revolution. Means a very small pitch on the spiral tool path. And also you might notice that I'm going conventional compared to climb. Climb would probably be a little bit better, but Fusion was not cooperating with the toolpath that I had chosen to go upside from the underside of the radius to the face of the part and do a climb mill path. Couldn't get my toolpath to behave, so just went conventional, and turned out it's not a big problem when you do grinding. At least not in this configuration. Here is another view on the grinding process. You can see the dust extraction to collect the gross amount of the carbide dust. So yeah, I'm not worried about the machine, and also the dust extractor or shop vac that I'm using is rated for cancerous and dangerous materials. Here you can see starting at the bottom of the radius and working my way up and outside towards the face of the part. In hindsight, this process is really stable, and after I figured out the first part, it was just load the part, touch off C height and hit go. Using some 1 micron diamond compound and a piece of hardwood chucked in my die grinder to give the radius of the bushings a final polish and blend the tool marks from the grinding process. This goes relatively quickly. The finish right off the machine was really good, but I figured the polishing itself goes very fast and doesn't hurt. Here's a close-up of 2 of the bushings. Left is the 2.1 millimeter and here is the 4.1 millimeter one. You can see that the radius after grinding on the CNC and a little bit of polishing, maybe 2 or 3 minutes of polishing with the die grinder on the lathe, really leaves a very nice finish here. Tiny edge break here. Same on this side, tiny edge break so we don't have a sharp edge. And on the back side, same thing, edge break on the bore and on the OD on both parts. Well, on all 8 of course, but I only have 2 in the picture here. And when we try to see inside, maybe you get an idea of the surface finish from the ID grinding, which is really not bad despite this jerry-rigged ID grinding setup. I think the surface finish is really serviceable. I guess I could polish it out to the same finish as the radius here in quite a short period of time, but as far as I understand, it's not necessary. I'm just doing the radius because it's very fast to do, and as far as I understand, something runs over the radius over here. So better surface finish doesn't hurt here. Here are the 2 the direct plated diamond tools. The grit is D125 or D126 that I use to grind the ID. The smaller one is 1.6 millimeter OD and the bigger one is 2.4 millimeter OD. These worked really, really well, and despite being fairly coarse, the finish in the bores is quite nice. This is the ball tool that I use to grind the radius. It's 2 millimeter nominal, but if you micrometer it carefully, it comes out at about 1.85 millimeters. This is a little bit finer grit than these. This is D95. The D95 or 125 gives the size of the diamond grain. On D95, the maximum size of a diamond grain on here can be 95 microns. There is a range to it. There is a fairly large range of the diamond grit size on here. I'll put it on screen. And yeah, this also worked marvelous well and still is in good condition and can be used to make more parts. We're in CAD and we have our 2 different bushings here. And here we can look at the tool paths that I created to grind the lead-in radius. It's a lot of blue because the individual lines are extremely close together. We're using a very small step over. Let's look at the cutting parameters. This is a surface morph toolpath. Let's edit. So I defined the grinding tool as a 1.85 millimeter ball end mill, basically. That's the size that I checked with a micrometer. Running it at full speed, 22,000 RPM. Yes, the spindle can go to 25, but I think it's good practice to not max out the spindle. The overall lifetime of the spindle will thank you. That comes from experience. We found at my former day job that high-speed spindles that you do not run at full speed live significantly longer. So 22,000 RPM, a feed of 1,000 millimeters per minute. This could be 2,000 millimeters too. you can feed them very fast. But on such a small contour, it gets very jiggly. The machine wants to basically tip over. And we're running dry. Geometry, I just selected the radius. And the step over. This is the important parameter. The step over is 2 microns. How do you come up with the step over for a grinding tool? It doesn't have flutes, it doesn't have anything. It's derived from the grain size. The tool we're using has a grain size, diamond grain of 75 to 90 micron. And general wisdom is that you can step over about 1/6 of the grain size. So let's take the smaller end of the grain size, 75. 75 divided by 6 is about 11.6 micron. That would be our maximum step over with the tool. I was erroring on the extreme cautious side and went down to 2 micron. First of all, I wasn't sure how the process is going, because this is the first time I'm grinding on the carbide on a CNC. And also the surface finish thanked you. So, and on the smaller one, it's the same deal. Starting all the way down here. And slowly working its way up towards the top where it exits the face. And the high depth of cut that the small tool takes has not proven to be a problem. There doesn't seem to be any tool deflection. The cutting pressure seems to be extremely low, especially since I'm taking a way lighter cut than the tool could give. So that seems to do well. These are all 8 of the carbide bushings with the lead-in radius. I deground to dimension. I ground the overall length off camera on the surface grinder, just putting them in a V-block and grinding the backside until the right length was achieved. The last step, which I'm also doing off camera, putting back in the lathe and just rounding the backside over with a ruby stone a tiny bit. So just so there is no sharp edge anymore. So I hope you enjoyed this little carbide project. That's not a material that I get to make a lot of parts with usually, but with a little bit of improvising, I think I get okay results. Thank you all for watching, and I'll be back.